The experiment that we're going to be doing this week and next week in lab is really all about how we can use color to determine the concentration of a solution. And the most important tool for us to use is something called Beer's law. Beer's law relates the absorbance of a solution to its concentration and its path length. So the simplest form of Beer's law that we can find is absorbance is equal to, let me do E epsilon times L times C. So abs is absorbance, C is concentration, L is what we call path length, and what's E? What's epsilon? Well, epsilon is just a constant, because if we really wanted to be picky about this, we would say that absorbance is proportional to path length time concentration. But proportions are nice concepts, but they're difficult to work with, so how do we get rid of a proportionality? By adding a constant. In this case, our constant epsilon is called by a number of names. The one I probably use the most is extinction coefficient. So Beer's law is very handy because as long as we can measure the absorbance of a sample and we know its extinction coefficient and its path length, we can calculate the concentration without having to know the concentration in advance. Another way we can think about Beer's law is a little differently. Let me erase my labels. What kind of a mathematical equation is this? Now, I can just about guarantee that any time a general chemistry professor asks you what kind of an equation is this, the answer is almost always going to be the equation of a line. Because lines make our job a lot easier when we're trying to analyze data. So, how do we make this look like a line? Well, what if that looks kind of like the equation of a line, doesn't it? So, why is there no plus b term out here? What's b in our line equation? That's the y-intercept, right? Well, if the concentration of the sample is 0, how much absorbance is it going to have? Well, it's going to have 0. So, a perfect set of data will follow Beer's law and give us an intercept of 0. Doesn't always happen, but it's something that we can look at to assess how good our data is. So it looks like if we keep the path length constant, which we can pretty easily do experimentally, all we have to do is plot absorbance versus concentration for some known samples, and we can calculate this term, this slope, epsilon times the path length. That's your experiment. So we've got 2 weeks to do this. The first week, we're going to figure out this value. We're going to generate our Beer's law standard calibration curve. So in week 1 of this experiment, you're going to prepare a number of solutions that you can figure out the concentration of, and you're going to measure their absorbance. So if we then graph absorbance versus, let's use a big M because we're going to use concentration in units of molarity. What are we going to do? We're going to prepare a number of molarities and measure their absorbance. And once we have our samples made, we can fit a line to that. We can get Excel to give us the equation of that line. And then next week, when we come back and prepare an unknown, we'll use this calibration curve. We'll use this line that we just fit to go the other way. And what? In that case, we're going to measure the absorbance. We're going to know M and B, and we're going to calculate the concentration of the solution that we make using our unknown sample of iron ore. So in order to do all this, we've got to do a couple things. First of all, we're going to need to use volumetric glassware to prepare our samples. That's one of the other videos that you're watching this week. We need to use the spectrometers. Well, you just use those for an experiment. There's another video if you want to brush up on how to use the spectrometers. And that's really about it. We're going to use procedures, techniques that we've used before. We're going to use volumetric glassware. And again, in the first week, we're going to develop this calibration plot with known samples. In the second week, we'll come back and analyze unknown samples using this data to figure out concentration. So there's not a whole lot that I have to talk about in this week's pre-lab. Again, it's all about this relationship, Beer's law. The only thing that we've got to be a little careful about here is, what did I say about L? I said in order to do what we're going to do, we need to keep L constant. How can you keep L constant in your experiment? Ideas? Well, there are two ways we could do it. The first way is to use very specialized and very expensive and well-calibrated tubes to hold your sample so that we knew the exact length of the path that the light was shining through. Or we could just use the same tube in the same orientation for every one of your samples. Because if you use the same tube in the same orientation, L is going to be constant. Now the place where people usually have problems with that is you're not going to know what L is. And that's okay. As long as epsilon times L is a constant, you don't need to know the value of either of them. All you need to know is that they're constant. So you're going to use the same test tube in the same orientation in your spectrometer to take every measurement, including your blank. So when you get to the point where you're generating this curve, make sure that you keep that in mind. All right? I think you can figure everything else out from the write-up, so good luck. I'll see you in lab, and make sure that you watch the volumetric glassware videos if you haven't already.